Okay, good morning, students. We continue with hoists and haulages. One could say that. And I assume that everyone, of course, has looked over the spot the lecture, just describing what a hoist is. You know, we just went over that in the last lecture, hoist, winches, and crane, what that essentially is. But this over here is something I want you to take note of. And what it essentially is applying the Allenbert's principle. And but this I'll touch on uh, uh, quite shortly when we solve. But this is the essential approach we take in solving these hoist and haulages problems, right? Okay, so I'll recap on this. But the idea is, let me just recap on it. First, we have to do a free body diagram for each individual item. Okay, so you might get marks, not you might get marks or might not get marks depending. But the idea is that for when you do the analysis, you need to break up each component and draw a free body diagram, right? So then it says, so for each object that goes under linear motion, you draw an FPD, show the forces, show the direction of the linear acceleration, and then apply the FPD to the equation F equals ma. Okay, we've done this before, chapter 1. So now, where the new section really comes in, this new part of the analysis is chapter 2. So for each rotating object, we also indicate on the free body diagram all the forces, and we also indicate the direction of the angular acceleration, and then apply the change in torque equals IA, right? So I have a question for you. Why do we always show which direction the system is rotating? Just a quick one. Anyone, quickly? Termanus, I think you know. All right, the reason why we always show the direction of acceleration is that so we know exactly where the rotational inertia will act against, similarly to the linear inertia and also the friction. So depending on how it's accelerating, we know where those two specific forces will be acting. Then of course, what we can do is set up an equation for each, right? And it's saying, and I'm going to highlight this and tell you if there are 4 objects, it's possible to set up 4 equations and just solve 4 unknowns, right? And there's three objects, 3 unknowns. So be aware of this, that you can end up with either simultaneous 3x3 matrix, highly doubt a 4x4 matrix. But I'm making you aware that you have to set up equations at some point, certain times. I think the more other problems, and you have to solve them at the same time. And of course, what's important, we are able to relate the acceleration. So for instance, additionally, since the linear acceleration of a point on a row passing around a drum is related to the angular acceleration of the drum, we can make use of linear acceleration equals radius times angular acceleration. You see how we will touch on that. Okay, we'll come back to this. I briefly showed you, this is what I wanted you guys to do. I showed you this example, end up with a 2x2, and eventually we basically solve this problem applying exactly what's said. So this example, this is what we're going to start with today. Example 2 in my slides is in your book. It's the first example on hoists. And this is what we're going to be doing. Like I said, two, hopefully 3. First prize is 3. Okay, I'm just going to get my blackboard here. Oop. So this is the one we're going to do. So it seems daunting, but it's really not. Okay, so I'll just quickly share a question now. So I recommend getting your pens ready, calculators ready. All right. Okay. So, like I said, this is on page F4. If you are interested. But this approach is a general approach on how you approach all these problems. Okay, so a load 230 kilograms lifted by means of a rope, which is wound several times around the drum, which supports a balance mass of 140 kilograms. As the load rises, so the balance mass falls. Obviously, the drum has a diameter of 1.2 meters and a radius of gyration of 0.53. When we hear that, we know we have to find the rotational inertia of the drum, and its mass is 70 kilograms, right? The frictional resistance to the movement of the load is 110, and that to the balance mass is 90. So this friction resistance, obviously, sometimes we neglect it, by the 230 kilogram mass and by the balance mass of 140. The frictional torque on the drum shaft is 80 Newton meter. Does anyone have an idea where the friction torque comes from? So we've got this drum. Yes, thank you. And we've got a shaft in the middle, of course. Of course, it's definitely coupled to a motor. There could be a transmission system, a gearbox, one could say, and then that's coupled to a motor. Frictional torque, anyone? Off the cuff, Mr. Seb? Can you guys hear me? In the bearing, fantastic, fantastic. In the bearing, yes. Of course, it's housed in the bearing. Shaft is housed in the bearing, and as it turns, to surface the rubbish on it, and you're gonna be losing some torque. Fantastic. Okay. So, objective is to find the torque required on the drum and the power required at the instant when the load is an upward velocity of 2.5 meters per second and an upward acceleration of 1.2 meters per second squared. So this is the important part, right? Worry about that for now. So this is accelerating at 1.2 meters per second. So what we do, like I said, we have to now sketch our system. So I'll go step by step, right? So this is the, so like I said, isolate each component and then analyze. So we know that this is the 230 kilogram mass. It's going upwards. This guy is rotating that way. Of course, come back to all of this now, and this is 140 balance mass. Okay, so I'll say, let's say I don't know, I'm gonna call this guy T1, right? So I'll say for 230 kilogram mass. Yeah. Okay, first thing what we do, we isolate the component, right? All the forces acting on it. Of course, it's mg. That should be correct. The mass is always acting downwards. We've got T1, of course, that's a tension in the rope. And we know that it's accelerating upwards, right? So I'll follow these diagrams concurrently. That's A, I can label it here. And we know that's going up. Therefore, our frictional force should be, you could call it F mu, or you could call it FF, doesn't really matter, so as long as you know what it is. F mu here, F mu1, we have another one, and we have also our inertial force, right? Fz, we call it Fz1. Okay, because Fz2 will be on the other side. So give me a second. What's happening here? Give me a short moment. Okay, that's resolved. All right, so do we all agree with all these forces on the body? If you agree, just send me a thumbs up. Thumbs up, thumbs up. Fantastic, thank you. Yeah. It's all straightforward for now. It is actually straightforward. So we're going to find T1. Right, I didn't mention T1. So what is T1? Okay. So sorry, students, before we work out each and everything here, what we're going to do is to find the total torque on the drum. I actually want to start the problem on this, so just coming back to me now. The total torque on the drum, right? So I'm going to say T total. Hey, no, man. It's going to be, it's going to be the torque produced by the 230 kilograms mass, right? By the 140, and we're going to get a torque difference here. So I'm going to say it's going to be by the masses, by mass. I'll just say by the masses, of course, you know, it's the balance, plus the inertial torque. Just write it like this. Plus the frictional torque. So what we're essentially doing is going to find the torque by the masses, torque, the inertial torque, which will be easy, ik squared times the angular acceleration, and the frictional torque, which is given of 80. I'm just trying to, I think what I wanted to do was, with that, is to give you a holistic picture to where we working towards. So the idea is that we wanna make the system work, but we need a certain amount of power to make it work. So if you choose the wrong motor, for instance, and you expect this thing to turn and it doesn't turn, these are the reasons why. So you have to find the total torque on the drum, and then so from that you can find the power, and you have the power, you can select the right motor. All right. So back to our F equals MA. So we can do that. Alternatively, of course, we can just, you know, if you want to be really cool about it, you apply that. You can say T1 minus F mu minus Fz equals MA. Right? That's the normal way of doing it. Of course, you've got to just added them all, I think. No, why is this not right? T1, that's going that way, it's positive. Okay, regardless, you apply that, T1, that's going to be equal to F mu plus mg plus inertial force. Okay, so F mu is given, that's at 110 newtons. The mass, that's the gravity, 230. Oh, I don't know how the newtons there. And then our inertial torque is the acceleration, all right? So it's 230, and we have an upward acceleration of 1.2. Okay, can we just quickly compute that? I hope that should give us the right answer. Two six four 2.3 newtons. Okay, are we all happy with this one? Basic, right? Mr. Doyle, mornings. Got around 2 marks there. Students, can you hear me? Robert.
I can hear you, sir. Good morning.
Oh, fantastic. Okay. People waking up. That's in the morning voices are here. Okay, so once we get that, now we move on to the drum. So I'll say, can I just come over here, rather? I'll say for drum, right? Say for drum. Okay, so again, if you look at the drum, just gonna, here we go. Thank you. On the drum. Okay, so before we get to the drum, like I said, the first thing is we look at all the linear parts, right? Okay, so because we first want to find the torque by the masses. So we're going to say now for 140 kilogram mass. So this will be on that image. So now we isolate this guy. Acceleration is going downwards in this case, right? We've got that. Okay, I'm not going to write that there. We've got T2 over there. Okay, so free body diagrams are essential in this thing. So now acceleration is going downwards. We've got our T2. We've got our standard mg. Accelerating downwards. You have your F mu going that way, and you have your inertial force going this way. Like if you just do a standard balance for this, that'll be T2 plus F mu plus F, Z equals mg. Fantastic. Okay, so once that is there, we can the objective to find T2. So it's going to be mg. So mg is 140 times 9,81 minus F mu. So for the balance mass, the friction is 90, as it says there, and that to the movement of the balance mass is 90. That's a frictional resistance, right? That's 90 minus Fz. So that's going to be 140 times 1.2. What do we get for that, right? That's a tension in that rope. It's also important when you design these ropes, they are able to withstand those loads. So what is my T2 value? I'll give you guys 30 seconds quickly.
115.4. That's what I got.
Sorry? Great, I'm something. 115. Yeah, there we go. That looks right. 111 5.4. All right, so those are the tensions in the ropes. Oh.
Yeah, I just missed something quick.
Yes.
I just missed the why the frictional force in the two equations different.
Oh no, it's essentially just given here,
on the
right?
same drum.
It's no. This is the frictional movement for this over here for the specific one.
Oh, okay. Are they in a sleeve?
Yes, but I see you. I see where you're coming from, but I mean, we're just taking this with a pinch of salt, essentially. Because I mean, you could argue and say that it's the same friction. Because I mean, if it's how can I pull here? I'm with you like that. Let's say this is a rope here. I don't know if you. You know what I mean? And I hear what you're saying, but I mean, it's just I guess it's an exercise of the making it different, and it could possibly be obviously because it's the frictional force is a function of mu times n, right?
Yeah.
And of course, that is mg. So of course, the bigger the mass, the bigger the frictional force, right? Does it make sense?
Yeah, it's true. But also, just because the two weights are connected to each other, and they're using one cable, whatever frictional force the 230 kilogram has to overcome, the 140 has to also overcome that also because they're connected. And shouldn't T1 and T2 shouldn't T1 and T2 be the same value? Because in all the other D'Alembert principles, T1 and T2 was always the same because they're connected to each other.
Now you'll see now what we actually was looking for the torques of the drum. I hear you, but it's not the case in this one. So yeah, we'll discuss more. Just give me time. Give me time. Now, because normally if you find that tension, it's not the case. But we'll talk about it. And the reason why it's not so simple, remember, there's a lot of things, there's talked about a frictionless pulley. We ignored a lot of things in those problems. That's why. But now we kind of embellishing it to a more realistic kind of thing. Mr. Kiefer, because normally we say, oh no, neglect this. You assume it's the same, but this is the point of this kind of analysis, that becoming more aware that it's not simple. Anyway, so we need to find the total torque on the drum, right? And so what we have to do now is, well, we have to find the net torque produced by the masses. So okay, they call it, I don't know what I should call it over here. They call it torque RD. So we can label this torque, it's reaction torque on the drum due to the thing, torque RD. We can call this TZ, and we can call this T mu or TF. Really, it's up to you. Okay, so to find the net torque on the drum, because this will be over here, and of course this will be over here. That's T2. So T1 minus T2, this is going to be TRD. So it's just a very simple thing. We're just subtracting the two torques, and then the diameter was given to us, and that was at T over 2. It's a very important problem, this one, just giving you the overview of exactly how this works. So we have 264.23 minus 111 that, and the diameter is 1.2, so that's going to be 0.6. So I'll just write it as that. So when I'm looking at this here, if I want to make sense of this, I would have initially thought something else, but okay, I'll just take what they have here. I'll get back to that again. So this is the torque produced by those masses, right, on the drum. Very important. Well, I'll try to show you how integrated these problems are, but anyway, just bear with me. So the Kiefer is really concerned about these tensions being the same. I was not. So what we found, due to the masses, we found out that 916.14 Newton meters is experienced on this drum over here, right? Okay. Tick this off. So this is all going to be fairly easy. The next part, like I said, we have to do the inertial component, and we can call that TZ. And TZ is fairly simple. That's just going to be IZ, or I, or the drum, times K squared. I'm sorry, not K squared, I times angular acceleration. Very important relationship you've learned. So I, of course, is your mass of the drum, which is given to as 70 kilograms. The radial acceleration also given to 0.53 squared. And then your angular acceleration, and that is what I was talking about in the last point of the slides, what I was mentioning, because there's no slipping here, obviously. So we can relate this, and of course, A equals R times alpha, and we want this, so we know that's 1.2, and of course the drum's diameter is at 0.6, and then we can get our angular acceleration. All right, so if you do that, that's 70 times 0.53 squared times 1.2 over 0.6. So I think you should get 39.326 Newton meter. If the question is still feeling uncomfortable, that's perfectly fine. You'll start to see once we do a few more what's exactly happening. Just bear in mind. It's just important to understand how to find all the tensions, find the torques. So holistically, for this, we have the drum over here. We've got that producing a torque, that tension, right? So we found this net torque, so to say, and it's spinning this way, right? Therefore, we have, so our angular acceleration is going this way. And we're going to have TF or T mu and TZ. Let's just call it, just recall this. That's just T mu. And the reason why finding this, I'm going to ask you a nice question now. I'm going to see if you guys are able to, I'm just going to be smart to get it. Okay, so we found these. We find the total torque, which is required by the shaft, obviously, to rotate this. Shaft has to turn a specific, it must turn to rotate this whole drum. The bearings over here somewhere. Nevertheless, let's find T mu. Is T mu given to us? Yeah, the frictional torque on the drum, luckily for us, fortunately for us, given to us, and that's 80. So what did I tell you? The total torque of the drum. And now that's the question, right? So we don't know. Total torque on drum. Can someone give the total torque on the drum quickly? Quick. We've gotten fantastic 1035.466. Fantastic, right? That's that. Now, of course, they've requested power, right? And power is equal to torque times omega, the mechanical power, or you could have done power equals force times velocity. It's entirely up to you. But of course, which velocity do you, so now anyway, so the torque is this 466 omega. So they gave us our linear speed, if you remember. It's 2.5 meters per second. And we know that V equals omega R. So that's 2.5 divided by 0.6. And if you compute this guy, you should get 4,3 something. So it's going to get fun now. Don't worry. 4 kilowatt. Are we happy with this? I'm looking for something nice. Do we all get that? So, hey, I just can't find something nice here. No, I'm not getting it. Okay. So there are two additional things that I'll make you aware of. What I might ask I hope you're paying attention, is, so I have an appendix here. And I might ask, which motor will you select for this particular, which motor will you select for this particular application, right? And which motor will you select? And of course, there's a catalog. This is all three-phase induction motors. So I'll give you these options, and which motor will you select? Anyone? So we've got 4.31 kilowatts. Hey, I like this. I like this. Fantastic, the 5.5 kilowatts. Yes, this is what I want to see. So the question might be phrased in a way where you have to select a motor, right, as a second engineer or chief. So you know for a particular application what motor to basically get. Of course, it's not as simple as it seems, but it's a very good starting point. Another question for more for the big guys, right? The big chiefs and chiefess, or I don't know what you call them, the kings and the queens. So if I say assume the shaft is has an allowable shear stress of it's a solid shaft, or maybe hollow, but definitely solid, of, let's give it a value of, let's say, what should I have it as? 1. Let me just quickly check. I'm embarrassed, I can't remember the top of my head. It's around, some give a shear stress value there. That's too small. I'm looking for a typical shear stress value. Something about 0.57 shaft. Yeah, I'll just say, where's my task book? It's not even here. So I'm making you aware that I'm going to bring some strengths into this to see if people are sharp here. Yeah, let's just say 230, 235, you know, just be safe. I don't know. So fairly, 235 MPa. What is the diameter? What diameter will you choose? So we've got on a motor. Of course, the diameter is also dependent on the motor, obviously. If you have to couple it. But the question is, what I'd like to know the process you think about in selecting the diameter of the shaft. Are we all still here? Is it too early for this kind of question? So these are all the extra marks I'm making you guys aware of. Ivano, Mr. Neto, Charlton, Samar. So you get torque, it's 5/16 d squared shear, right? But now, what's also important to note is that the torque by the drum is probably the mean torque, right, produced by the drum. So then depending on application, of course, I probably have to give it to you. I'll say assume 25% from mean, right? So all you have to do is say 1035.466 times 1.25 over pi over 16 times allowable shear 235 root this I and make this d, sorry, it's cube root. So this is I want you guys to think about engineering problems never in isolation. I mean, for the subject I do understand, but when you integrate them, hey, thought so. I'm gonna readjust my value here. Just please give me a second. Oh, I'm choosing the wrong thing here. You guys get the diameter? Chose the wrong thing here. It is a strength of material type of question. I'm throwing in here for bonus, for extra mark, for the ones who are serious. I'm trying to integrate the concepts for you so you can understand all of this is not in isolation. It is part of strengths. Okay, and if you get the answer, what do you get? It's 30.384 millimeter shaft. Mr. Seb, what's the standard size shafts? What shaft can we choose? What are the sizes? Students, are you still there? Is there any questions? Students? Any questions?
Mr. Scow, I'm still here, but I'm following the lecture from the cell phone, and it's very small and everything, and I cannot really even see. But what you are writing on the pen, I can see.
Okay. No, so what I'm asking is basically so now we've used all these values to kind of find a diameter, well, you know, and I just asking you what's a standard size shaft. I mean, you get standard size shafts, you don't get a 30.8. Yeah, no question from me. So guys, the whole point of this is just showing you a small idea of how I could ask you determine the size of the motor, and once you find the total torque, get the velocity, you can choose a motor here. And also as a bonus question, maybe I would ask the size of the shaft. This is just to make things interesting, right? So anyway, let's move on to the next example. I assume there's no questions, so I can do the next one. Now the next one is very important, students. That's very well put out. Oh, let me go back to my slide first, and then. But the next one you really have to pay attention, because it's going to introduce something not new, but okay. So that is the example here now. So guys, so normally these Hoist haulages, even your car as well, your transmission system, it of course consisted of a gear train. Now in MOM 3, you'll be analyzing gears in depth. So that's where, I mean, probably for lecture MOM next year, I'll probably have gears first. So, but basically, you do a lot of analysis on gears in the next level. But what's important here is that the efficiency of the gear train. So this is something which is going to be introduced now within your commutation. It's a very small introduction, but it's just important to understand, right? So let's say any mechanical component system, which is moving parts, has friction. This friction is converting foreign into heat, right? Which is dissipated in the surroundings or the slashed environment. Therefore, it's lost. So this, of course, is due to the faces of the gears teeth in contact with each other. So the gears touching, rubbing each other. And also the bearings, which houses the shafts, and as you turn, there are some friction losses. And these are the friction torques. And also, that's where the frictional torque essentially comes from. And of course, what we're looking at is the efficiency of a gear train, right? And it is typically due to the gear teeth contact. So what I have here basically is a simple sketch there with your driver gear and your pinion and your so-called driving wheel. One is turning, the other one rotates the other way. You get a specific amount of torque in and speed in, and of course you get a specific torque out with an omega out, right? What is essentially important on this whole thing is that there are two additional parameters which you have to account for, which is the gear ratio, which is omega in over omega out, and your efficiency of your drive. So we're going to do a question like this, and so you would basically see it'll be a more realistic question because most systems have transmission systems or gear reduction systems, right? So it's just important to note you have to factor in omega and you have to factor in as part of your in your calculations. When you especially when you're going through the reduction system. It's nothing big, it's just something small to note, right? So how it typically works, there's a small example I want to do for you guys. Just give me a second. So let's say an electric motor, as that guy over here, is operating at a specific speed and a rated torque of 100 Newton meters. So it's driving in a machine through a gearbox, N equals 24, and efficiency of 80%. Determine the power reached in the driven machine under steady operating conditions. So the idea here is I just put up this picture so you have a motor. It's driving this transmission system in the middle. I hope you guys can see that. And we're assuming it's some typical conveyor system over here, right? Let's just say that's the driven machine. It could have been anything. So what we're just looking for here is the torque, the power reaching the driven machine. Okay, so I think I have a blank page next here. Yep. So just writing the values down. So omega is 144 RPM. So I just want to have that's omega. Torque, I don't know how the color changed now. It's 100 Newton meter. And what's the other one again? And then we have our N, which is the ratio. And then we have efficiency of a drive, which is 80%, right? That's very important. So what I want is the power coming out. So let me just copy and paste that sketch. Yeah. So what we're looking for is the power on the other side, basically. Simple. Nothing big. So to find torque out, right? If you get back at these models over here, these equations, so what you're expecting is that so T in equals T out over. Okay, let me just do it like this rather. Okay, just I'll show you how it's all derived first of all. For the sake of peace. I don't actually want to spend too much time on this over here, but just it's worth spending time to understand. Now it all starts basically, we have the efficiency is known as power out over power in, right? Too lot. I'm not sure. I'm saying it's too much. No, it's just a small concept. It's not really. Don't worry about it. You'll get it. So we have power out over power in, which is essentially equal to W out times T out, W in times that, right? But we know that your reduction is your gear ratio is essentially W in over W out, and if you flip it around, you get 1 over N. So this becomes here 1 over N, right? So the efficiency equals T out over T in, and we have N, and we have 1, right? And what we're looking here is now, then that's how the equation looks like now. Efficiency equals, or yeah, T out over N of T in. So if you want to find T in is basically going to be T out over omega N, or T out will be that. So now in our case, we've got the input torque. So what are we looking for? Or will T out to be right? I think. So the question is, the question which I had now. So it's a very simple setup, man. Don't worry about it. I just want to explain to you exactly what's going on here. So we want the power out, right? So I think the first thing what happens now is that our torque out, I mentioned to you, it's this times that times T in, right? So it's simply 0.8 times 24 times 100. That's your torque there, right? So let's get that quickly. The torque out is 1920 Newton meters. Okay. What's next is, of course, your omega, which we need. And omega, if you remember that, it's a gear reduction system. So it'll be W in over W out, right? Simple thing. No criticalness. So W in, now I mean, this looks really bad. W in over W out. Now the book doesn't even explain this properly, so that's why I'm making sure I'm going over it. But anyway, so if you want to find W out, it's a simple calculation. Obviously, it'll be 1440 and divided by 24. So can you see what happens here, right? That's what the reduction system does. Our torque increases and our speed decreases. Torque increases, speed decreases. So that's the purpose of motor spinning too fast. You know, on all that speed. So what do? We have a transmission system, so we can get more torque out. That's the whole point. And if you want to find the power out on the other side, that's going to be simply 1/2 torque times omega. So torque was 60 times 2 pi over 60. And if you find the answer, what will you get? 1920. 60 times 2 pi over 60. You should get 12.064 kilowatt. All right. Is everyone happy with that? So it's a small thing, but it's not mentioned to you in the notes, but I made a point of telling you guys how transmission kind of system works. So make sure you recap over this particular concept. It's normally integrated into the question. Are we all okay, guys? Can I move on? Any questions? Hey, people are quiet. This is not what I expect from my students.
I think everybody's doing the naval architecture tutorial.
Oh, it's for today?
It's for today at 1800.
Is it? Wow.
Yeah.
Okay.
And we only got it last night, 1800.
I know.
But anyway.
Yeah, I see.
Oh, and so 2 lot is the shorthand for second law of thermodynamics. Your power in is equal to your power out, and that's where we get this TW equals TW. But because we have the efficiency, we have to multiply it on the other side.
Yeah, but it's the first law, not the second law, by the way. Second law is the law of entropy.
Oh, okay, sorry. Then it's 1 lot.
No, it's cool. That's cool.
Right.
It's cool. I like it. No, just a small explanation of what's happening over here. So so now, guys, we are going to be doing the apex problem here, and it's this one. It looks daunting, but this is the kind of level which you're required to basically to be at, right? So I'm going to prepare this question, and then we can solve it, and then we can call it for today. Next week we start on simple harmonic motion. I might probably do another always problem next week, just one, and then you guys can yeah. So next week's gonna be a bit of a hectic week, but it's fine. I'm here, so it shouldn't be a problem. Okay, so guys, this is a very good question. So we have a motor, gearbox, a hoist drum, an idler drum, and a load, right? So we have to do exactly what we did in the previous one. And in this case, what's happening here is that this load is being hauled across this plane here. So it's the movement is going this way, just in case normally the movement will be given to you, right? So the question is, what you want to find is a motor output torque. So you want to find this guy here, T out, right? That's the output torque. Am I correct? Yeah. So you want to find to accelerate it at that particular acceleration. You want to find it. So I'm going to give you guys. You can either have a 5-minute break, because I mean we are concluding at 10 past. And of course, I don't have to move at slow. I can move it fast, as I have experience. I'd like you guys to quickly find for me, and please try as fast as possible. Find for me F1, which is find the force in this part here. So I'm going to call this guy F1. So acceleration is going this way, guys. Speaking your way. So you start applying F equals MA. And then try to find me also, if you can find F1 and find F2.
I don't think you wrote anything, sir.
Oh, sorry. It's my bad. I did, but it's on the whiteboard. Okay, so I'll just say that again. So I'll just prepare that. So simple. Again, find me the tension in this chord, the tension in this chord. You can call it T1 or T2. I'm just calling it F because it's a force, and T we use for torque in this case. That's perfectly fine. So you apply that over there, and you apply for the idler drum and try to get that F2. Okay, guys, I'll give you like around 5 odd minutes. Please try to do it. It's to see if you can understand. So start with the horizontal load. You move to the idler drum, and from the idler drum you go to the hoist. From the hoist we go to the gearbox, and then to the motor. So this question is nicely broken up, and I'm making you aware of it. The questions in the notepad, they normally integrate this whole section into one, so it looks a bit messy for you, and you really can't see. So what I'm doing here is I'm making sure that you guys understand, like all the individual parts. It all makes sense once you do this problem. Regardless, just have a go. So I'll give you guys 5 minutes. Yeah. All right. There is enough time. Or was it enough time? Do you guys get it for one? Anyone get F1? Hello? 1.1? No, it's incorrect. Or 1.1? Definitely not 1.1. No, impossible. Are we talking about the same thing over here?
So maybe you have to work it for us.
Yeah, I'm definitely going to. I thought you guys were giving the concept. Okay. Hey, I'm hoping for the best. Oh, it's that cat laughing. Okay. So guys, just on the horizontal plane, right? You apply, like I said, it's, F equals ma. Once again, we're given the acceleration of the thing. Okay, 1.8. Simple. We've got F1. So okay, let's do the analysis of each one. Sorry, I'm rushing. We've got that on the horizontal plane. We've got that tension over here. F1. So we see the acceleration is going that way, right? And it's going that way. We've got a frictional force going that way. Right, and of course we've got our inertial force going that way. Right, so we know that F1 will be equal to F1 will be equal to F mu plus Fz. I hope you guys did that. I mean, comment more difficult than that. So we've got a frictional coefficient, so that's 0.4. Normal force is 500 times 9.81. So if the girl wants to haulage that this particular thing, mass, load, whatever that is, and you've got our Fz, and that's 500 times 1.8. Mr. Kiefer and Annalisa, what did you guys do? Because you're making me laugh here. I don't know how you managed to. You guys got that.
Yeah, no, sir. Can you believe I forgot to times gravity?
I forgot.
What did you do? No, man, guys, come on.
I mean, no, I forgot friction.
Oh, Mr. Mzam, I'm glad you laughed. What's going on? Yeah. Anyway,
where do you do you get 0.4 from? I don't see the coefficient of friction. Oh shit!
Oh, sorry.
Good lord.
Yeah. No, it's fine. It's my fault. I mean, you guys didn't have a full idea of the schematic. Okay. But like I said, if you can do something like this, you'll be sorted, and you'll see why. Okay. So Doyle. Happy. So now we move to the idler drum now, right? We can call this for load if you want. This is for the idler drum. People are awake now. So of course the idler drum looks something. Okay, let me first draw my circle. My drum, sorry, my circle. Oh man. Yes, there we go. I was going to make my line straight as well. I might be asking too much. Okay, so accelerating this way. Sorry, this way is clockwise. Here we have, you call this F2, right? That's F2, and we have F1. Okay. So in the last one, we find the total torque on acting on the drum, but of course we'll more focused on this end to find you know, we're going to the motor now. All right. So what we need to do now is you have to apply. Oh, of course. So what else is here? We've got a frictional torque. So T mu, and then we have also our inertial torque, Tz. Okay, our rotational inertia to overcome that inertia. So we can apply now torque equals I times alpha. All right. So the way I do this, okay, F2 is going clockwise, so that's positive. So that's going to be F2 times the dimension of the drum, which is 0.8. No, that's the radius. That's the 0.4. Sorry. which is the dimensional time is 0.8. Sorry guys, I know it's a bit, some of you guys on your phones, that's a bit crappy, but it's 0.8 minus, so we're just adding all the torques here. Of course, we've got F1. What's F1 doing? F1 is going anti-clock, right? So F1 is going to be 2862 times 0.4 as well. And then we have TZ and T means always negative to the actual torque what we want. Anyway, we know this. TZ, so now what we have to do now is find I, of course. And I is going to be mass 280 times 0.36 squared, and 280 times 0.36 squared gives you 36.288 kilogram meter squared. That's the rotational inertia. But of course, TZ is equal to I times alpha. Very important. So that's going to be 36.288 times, of course, we can relate the angular acceleration to the linear acceleration. That's going to be 1.8 divided by the radius of 0.4. And the last guy we need is a frictional torque of minus 60. Right? And that equals 0, and then we can solve for F2. Right? So that should be simple, right? I think that's simple enough. Let's see what we get. 60 plus 206. Students, are you getting the concept of what's happening here? I don't know if you guys are all with me. I'd like to hear some words. I don't know. Something from your opinion on what's happening.
So it seems that for this thing we're working backwards from the force till we get to the motor to determine what the torque that we need for the motor.
That's fantastic. That's the idea. Yeah, getting it. That's exactly. It becomes a bit more easier now. Yeah, that's exactly what we're doing.
So we are in all questions like this, we're always going to be working from the load backwards towards the motor, or will there be cases where we have to start in the middle and work both ways, or work from the motor to the load? Or
so Doyle, very good question. Honestly, if you saw, I was kind of leading you, especially with the previous question. You're always going to work from the load to the motor. That's so I can check, so you guys can select the motor in the shaft. I'm kind of leading you there. Does it make sense? But you can do the questions where you can find the load. I am making a review of that as well. That's possible. I did put some questions like that in, but obviously I have my own touch, which I wanna. But you can do it both ways. I'm making you aware. It's possible. Yeah.
Sure.
It's not
okay.
that
Thank you.
Yeah. Cool. Thanks for your question.
And sorry. My video and audio cut out there. I had a bad bit of internet, but the sum of the T is equal to IA. That I is the what is that I there?
That's your rotational inertia. This the TZ.
Sorry.
Do my this over here.
Wait. Where are you? No, I'm talking about where it says sum of T equals IA.
Oh, yeah. Oh, that's so. I'm just applying Newton's second law essentially, man. For the it's the same thing over here. I'm just making it. I'm just writing the standard first formula there. You could have essentially just not written it, but I'm just showing you what I'm applying. Does it make sense? Like I'm applying that. I could have written this as F1 minus F mu equals Fz. I'm just showing you for this here, man. Are you with me?
Right.
Same thing. Yeah. I'm just
somewhat.
Okay, so Doyle, normally when you apply Newton's first law, you have this kind of setup, the elements principle. It's always equal to the inertia. So if you look at the first body, we have F1, then we have minus F mu, and we always essentially make it equal to the inertial the inertial force, or Fz. But it's exactly the same as just saying, okay, just look at the weight of forces on the left-hand side equal to the force on the right-hand side. You're going to carry over this, and F1 will still be Fz plus F mu. Are you with me?
Right.
It's the same thing.
Which we found already.
Yeah. So I'm just being fancy when I'm writing sum of torques equals. I'm just showing I'm applying the second law essentially. Yeah. I will not penalize you if you do not write that. Yeah. Okay. So we found F2, and thanks for the question. So now we have to move on to the hoist drum, right? Okay, so the hoist drum. Well, it says hoist drum. I'm just going to give me a second. Let me just get this right. Hey. Okay, hoist. There we go. Thank you. And so we've got now our F2 coming in, right? That's our F2. And of course, you'd say that she's rotating that way, or accelerating that way, sorry, alpha. And of course, we're going to have our TZ and our T mu on this drum. Oh, we're going to call this F, then we're going to have, what you're going to find here, I'm going to call it just, how should I put it here? I'll make it like this. Just bear with me here. But it's going to be F3, which will be, just zoom in again, it's basically the torque out of the gearbox. So this is what you're going to see now, torque. So I'm going to call it F3. So this is torque out of the gearbox, and that's how we're going to apply that formula we just did earlier on. You can find the torque in the input torque of the gearbox is the output torque of the motor, obviously. So yeah. Okay. Anyway, we apply exactly the same thing again. We can have F3 times, so the diameter of the hoist drum in this case is 480, so it's 0.24. I could have arguably just left this and called it T3, torque number 3. I'm just letting you know because we actually care about the torque. So I'll keep it T3 minus F2, of course. So F2 is going to be 3420.24 times 0.24. By the way, guys, this is my second favorite section of this particular subject. First is mass moment, like the shapes and stuff. Nevertheless, we've got a frictional torque of minus 40, and we still have to find the inertial torque as well. And for the drum, I'm going to have it over here. So the hoist drum, it's going to be 90 times gyration of 0.2 squared. So we get that 90 times 0.2 squared is 3.6 kilogram meter squared. 3.6, and of course we have to times it by alpha. So this I to get the torque, and in this case it's 1.8. Remember, if you have to use the hoist's drum's diameter now, and that's radius, so that's 0.24. And if you find that, you should get so that's 3.6 times 1.8 over 0.24, 27, I think. Yeah, 27 Newton meter. So we have 27 Newton meter to overcome inertia. I am speaking. Yes, can you guys not hear me? Yeah, it's probably have to refresh. So that's fairly simple, minus the 27. Okay, that's over here equals 0. Okay, let me just erase this. Okay, so like I said, I'm not gonna find F3 now. I just care about torque 3 here because I need the torque essentially. And that's gonna be now 3240.24 times 0.24 plus 40 plus 27, and you get a value of, am I missing something? I feel like I'm wrong. 24 minus 40. Someone's saying something here. Something went wrong. Oh, it's okay. So I'm getting a talk, guys. I don't know if you guys got it. I don't know if I missed something here. So we're just adding all of these guys up. Plus 27. I'm not getting the exact answer here. Just give me. Oh, I didn't square this. That's why. I didn't square that. That's why. Just 1.8 over 0.24 squared. Sorry, this answer. This is not 27. This is 202. There we go. So it's 3420.24 times 0.24 minus 40. Sorry, plus 40 plus 202.5. Oh man. What talk do you guys get?
Sorry, so where is that 40 and 202.5 from?
Oh, what's going on here? So just erase all of this. Going back to the drum. So we're always going to get on each drum the inertial resistance, rotational inertial resistance, obviously on a drum, which we can compute by saying 90 times the radius of gyration, which is K. I think that's where my mistake is. And then, of course, the frictional torque on the drum, because it's on a shaft and it's housed by a bearing, we get that. That's where it comes from. So each individual drum has exactly the same parameters, but of course it differs depending on the size and all of that. Does it make sense?
Yeah.
And Elisa?
Yes,
Are you
I
there?
got it.
Okay, yeah. So it's just dependent on what's given on the actual thing. So I'm just checking my torque here. So I'm not really happy with the values I'm getting. My angular acceleration is, why am I squaring this? That's the thing. It's not. It's this is wrong. So it's torque, your inertia times one. Your angular acceleration is 1.8 divided by 0.24. You get 27 years. You get 27. Yeah. So TZ is 27. Oh, what's going on here? Okay, so I'm looking for, like I said, torque over here. This is T, not 27, equals 0. So I'm just essentially turning all of these guys over. Let me just make sure the answers are right. Plus 40 plus 27. Yeah. So it'll be 3420.4. I'm just getting this all over to the other side of the equation. Plus 27 plus the frictional torque of 40, which I removed here on mistake. Okay, let's just erase this as well. 24 minus 27 minus 40 equals 0. So your torque out of the gearbox is 8887.8576 Newton meter. So getting back here, I'm heading back to this particular section over here. You can see that F3 is torque out. If this, the T3 now, that's coming outside the gearbox, right? So if I'm going back to the gearbox now, well, I'm gonna draw my schematic for the gearbox. Whoop. Yes, zoom in. Computer's lagging for some reason. Where are we? So this is T3 that you got now, but this is also T out of the gearbox. So our gearbox had parameters of N is 30, and efficiency was 86%. And this is T, and we can call this T4 if you want. Okay. T into the gearbox. So we of course want T in, right? So to find that, remember over here we have a big torque and I think a slow speed normally on this side. So now what's going to happen is that our torque is going to decrease and our speed is going to go up, but we just care about the torque. So T4 will just be equal to the efficiency times N T3, right? This is just like on the slide, so that's 0.86 times 30 times whatever that was, 887.8576. Oh, is this correct? No. This is not right. This is not right.
You think you divide by efficiency?
Yes, exactly. That's why I was like, I'm going the wrong way. In this case, we're gonna have to go the other way, and then we're gonna have to say, sorry. Oh, undo. You're looking for T4. So this is the inside. So this should have been now in like that. So then T4 is going to be equal to 887.8. So it's very important to understand what we're expecting on the other side. So that's 0.86. Can we erase this? Times 30. So for what do we get for that torque? The torque in, and that's the one. So that's what we're actually looking for. The motor output is here, so that's should get 34.41, I think. So T4 is the motor output torque.
Yes, sir, 34.413.
Yeah. So just reverting back, guys, we've achieved the first part of the actual sum, and that's 34.41. Right? And now, of course, they want so we found the motor output, and they want the power. Guys, power is easy. It's not even worth our time again. That's just essential. And they give you the velocity of 1,440 revs per minute. So it's 34.41 times 1440 times 2 pi over 60. And you should get the value of 5.189 kilowatts. Right, there again, got to select a motor. There again, you can find out the diameter. Just making you aware. Just making you aware. Now, guys, before we depart now, so this is the end of the lecture. I want to ask you something now. This is the last part of the question, and it says, I want my doctorates in machines. So what change occurs to the motor output power once top speed has been reached? Who can tell me? What happens when the top speed is reached? Quick.
The power should be a little bit more.
More.
Yeah.
I don't think that's true.
Because when it reaches top speed, there's no more acceleration. So no more inertia that
Yes.
I have to overcome. So it becomes easier to continue going forward as opposed to
That's correct.
power down speed. So it should become more the power output.
No, the power is less. It's
Is it less?
you require less energy. That's what happens, Mr. Keith. Not
Oh,
think
okay.
about
Less
it.
energy needed,
Yeah.
so less energy put out.
Yes.
Okay.
And that is fantastic. So what I'm gonna leave you guys off with is that question. And what you have to do now is F is not anymore equal to MA. This man is good, very good. This falls away now because acceleration is 0. So sum of F equals 0. So what you're gonna have to do is redo all of this with no more inertia, because there won't be any more. Remember, we don't need any more inertia. We've passed that stage where we require where we actually require the extra torque to overcome inertia. So then you have to find again F1, F2, you know, F1, F2, T3. From T3 get T4. From T4 you can actually apply ingredient torque. So I hope that's clear to everyone. So I did post some exercises on Blackboard, and I might touch on, like I said, another example. We might continue with this because I have to start on simple harmonic motion next week. But I want to highlight to you so I'm only going to post the answers for that one, and then I hope you guys are going to tackle tackle the answer, just get that right. And then there's other examples planned to do. But what's important is that you go through all the examples in your textbook. That's from 1 to 5. You apply the stuff I've taught you. You do the exercise I always post on Blackboard. You know, all the extra stuff I normally post on Blackboard. Make sure you go over that. There's a few examples to do all that. And of course, attempt the exercises in your book for hoists. But ideally, start with this. Of course, start with slides. Go through slides. Yeah. Slides always first.
Sir, I have a question.
Yeah.
Yeah, regarding the question that you just did, I just want to understand. Like, okay. Regarding the question that we just did, so in that we're calculating the force, the tension in the rope, right? So so I want to understand the reason why you're saying it's different is because there is friction in each and every component, right?
That is correct.
Is that the reason?
That's the first one. Yep.
Okay. So also I want to also understand if is this the standard way to calculate it? Like you have to start from the load side until the motor side.
Yes, that is correct. But like Mr. Dole is asked this question, but there are times you're going to find one of the questions where they ask you which load you can get as well. So you start from you go from the motor and you go to the load.
Oh, okay.
Yeah.
Okay.
That's
also,
why, guys.
Yeah, I also have another question.
Yeah, Mr. Zam, you just have to wait here because I am something critical I want to tell you guys. So just keep your question. Okay. So guys, is it good news or bad news? I did mention I have good news for you guys, right? You guys remember I did mention the start of the lecture? Who can guess what the good news is? Quick.
We all passed.
We all passed the test. Yeah. You're not going to give us an exam.
No, the good news is I'm done marking your stuff. So I'll post your marks up. So I don't know if you guys should I post it now or should I wait till the end of the day? So I've done marked. All I can tell you is that the average mark was I think 51% for the first test. And I'll post the marks up, but I will be giving you. Now it's okay for me anyway. Yeah. I will post it up anyway during the course of the next few hours. So be ready, it's gonna come up. But I will be giving you comprehensive feedback by next week. Of course,
put everybody's names next to the marks, not just the student numbers.
Oh, of course, I will do that. I was going to ask that question, but I thought people are brave. But you know what? Yeah, that's perfectly fine. I will remove the names. Definitely. Okay, guys, thank you for attending today's lecture. I hope you enjoyed it. Please make sure you complete the what I just requested now. Make sure you have no acceleration. Get those tensions, get the new power of the motor. It's very, very important. Okay, guys, cheers, and I'll see you on Monday.
I think you forgot about the question.
Oh, yes, Muzab, what's the question? Sorry.
Yeah, I wanted to understand, like, if like you were to be asked to calculate the minimum power of the motor, how will you approach it?
The minimum power is when there's no when acceleration is zero, because you don't account for inertia anymore. So what you're gonna do now in that question, so I'll write it here for instance. We got a value of, what's the value we got for that motor now? The first one, or this, just check the black one. Yeah, we got 5,189, right? So that's 5,189. This is to start. This is the start, the max power you need. Does it make sense? To start moving.
Yes, sir.
Mr. Mzam, are you there? Mr. Mzam?
Yes, sir, I'm here.
Yeah, so that's to start moving, right?
Yes, sir.
But when you're gonna find the maximum, I'm not sure what the value is. It could be in the region of 3 kilowatts, I think. You're gonna find the minimum power is gonna be when, remember this is when you have M equals MA. Here, M equals MA is gonna be 0. So you're gonna have no inertia anymore. The system is just gonna be moving. So your power is gonna drop to around, let's say, 3,2 whatever, 2.5 kilowatts, for instance. That is what you're gonna find. That is your minimum power, and that is your maximum power. Remember to start something. Even in life, you got to think about it, right? In life, it's harder to start something, but once you get going, right, it becomes easier. I don't know if that makes sense to you.
So the only difference is that there is no acceleration.
That is correct. Think about it.
Yeah,
you know,
that's correct.
Yeah, and just think of life. You know, when you start studying, it's hard. I mean, but once you get back into the groove of the habits, it's easier.
Okay, perfect.
Yeah. Anyway, okay then. Cheers.
Okay, thank you.
No problems. Cheers. See you guys. Enjoy law. Bye.